partially shared with Complete Genomics, but it's basically a monopoly. We keep hoping that there will be another one, and there have been quite a few monopoly breakers. Someone basically broke 454's monopoly. This is the one that Hope Spring is known for. This is the oldest and slowest technology developed. So I'm not like giving these guys a break, and I was involved in it in the late 80s and still. But it is handheld. That's kind of cool. So even if it doesn't beat Illumina, it will allow you to do sort of real-time monitoring of your environment for, to see whether this room is full of H1N1 or something worse. And then free. And so there's a few different versions of this. The two main ones are one where you have a polymerase or helicase motor stripping off one strand that either goes through the pore. This is a kind of conventional single molecule pore ion measurement. This is Sagman and Nair, published on 1975. And here the conductance through the pore is modulated by the single strand of DNA. And ideally there'd be a narrow point that would detect one base. Typically it's more like 4 bases, so you get kind of blurriness when you have whole polymer runs. But you can see in this published data from some of these groups that you can't distinguish runs and C's from C's, C's, and A's. These have a distinctive picoampere conductance. That's one way of doing it. But you're kind of smearing together about 4 bases at a time, so to really distinguish it, you have to be able to discriminate 256 different levels. The alternative way of doing it is to, instead of running running single-stranded DNA through the pore, you can run it past the pore where the polymerase is stepping along, and now you're detecting the presence of a triphosphate rather than the single-stranded DNA itself. And then only as the triphosphate goes by does it perturb the signal. And I'll show you, so instead of getting these where you don't drop the baseline in between bases, you get something where you do drop the baseline in between. So these are intentionally difficult sequence whole polymers again, 4Gs, 4As, 4Ts, color-coded green, red, and blue. And you can see here, you get these 4Gs, and in between it drops, or goes back up to the baseline of 225 picoamperes. And they're discrete zones for these QD. Very speculative, still they are now, both of them are available. They're in labs being beta tested and producing data. The Oxford Nanopores produce data on the order for E. coli and yeast, and the Genia is about a few years behind them, but really just a few months behind them in terms of producing data. Now you can say, well, if we keep having this super steep exponential growth in capabilities beating Moore's law, then surely we're going to have problems with computing and with storage and with interpretation of other things. And so let's tackle that question of big data storage in a typically quirky way. So at the early days of these sequencing by synthesis, where you have these sort of randomly distributed amplified single molecules, each one of them be yielding fluorescent data. And so they weren't ideally gridded, and you had to collect quite a few image pixels for each piece of DNA. And so you'd have to collect maybe 100 types of information in order to get one base pair. Because a lot of them were black, a lot of them you had to collect around it to make sure it was separated from other data. And then you do it 30x coverage, which I already mentioned was caused many people to get in the project to freak out because it was 30x. Anyway, it's on the order of terabytes, many terabytes. But then, if you look in the computer science literature, if you do a really good job of sequencing, if you really get accurate enough sequencing that you can boldly throw away the image data, you can get it down to 2.5 megabytes. So instead of 10 to the 13th bytes, on the order of 10 to the 6th bytes, to store it relative to a reference. And so, and here's the reference on that. The reference, relative to the reference genome sequence, because you're just storing the differences, basically. You still have to store the reference, but that's small compared to this. And so if you wanted to store the entire human population of human genomes, so 7 billion times 6 billion, it's only 2 petabytes, so 2 times 10 to the 15th bytes, which is pathetic. I mean, the internet in a day will be using up 1,000 times that much in traffic, and even fairly simple computers handle this amount, and that's the entire human race. And in fact, we've gotten to the point where partly as an effort at irony, when people used to ask me, how are you going to store this data? And I just said, well, I'll store it in DNA. And then I said, well, I should take myself seriously. And so we started storing digital information that was not DNA sequencing into DNA, so kind of reversing the flow of information. And this is something I did with my own hands here. I am with purple gloves, and I was advised by my postdoctoral fellow, so he gave his job talk. He said I was his best postdoc so far, and I said I was also his worst postdoc so far. Anyway, I got first author on the science paper, and then since then, we're now scaling up to do it. We're doing a video with a major European data archiving company, and Sri at UCLA is doing an album for an amazing musical team called OKGo, for those of you who appreciate music. So we got data storage, but not quite handled, but I've shown you some of the issues around it. Data sharing's got to be even worse, and it's worse not just because it's big data, but because it's big human data. So I'm just going to quickly go through Jason mentioned this, and I don't want to hammer too hard on it. But here's an example of the personal genome project that Jason mentioned is now was chosen by the National Institute of Standard Technology and the Food and Drug Administration in a whimsical project they call the Genome in a Bottle. .org, which is to set standards. Anytime any new company wants to develop a new diagnostic, a new instrument, a new protocol, and they want to make sure that their tests that they're doing can be compared to other tests from previous and future methods, they'd like to know that their bottle of DNA came from the same prep of DNA. So they're doing 24 of these, so 8 trios, 2 parents and a child, and they looked all over the world for suitable samples, and I wouldn't be telling you this if they hadn't picked ours as the only project that was properly consented for re-identification and commercial use. And so all of the reference genomes will be from these 8 trios, which are intentionally very diverse in ancestral origin. And then there are many other projects that have benefited from this. We've worked with NIH ENCODE, which is a way of looking at all kinds of epigenetic data. We'll be more on that later, but we've provided them with literally billions of cells so they can characterize fibroblasts, stem cells, neurons, and so on, which was previously very hard for them to do. So now why is this project useful to so many groups? And it is because it is totally shareable. It is the most shareable data set in cells and synthetic biology on the planet. Possibly the world's only open access data set that combines medical data and genomic data. And that's because of the way they consent that they have to get 100% on the exam. It's a very simple exam at this point. It wasn't when we started. When we started the IRB, wanted everybody to have a PhD in genetics, which I'm glad we got through that phase quickly. That's no longer the case. We have regular people. And we have these biobanks that include stem cells, not limited to them, mostly through Coriell. And so here's some of my cells that have been redifferentiated, so dedifferentiated in stem cells and redifferentiated to neuronal rosettes as one of our favorite, and then individual bipolar neurons. And then this is my original brain before it was sliced by MRI. It was all virtual slicing, not actual slicing. And the other reason the project is good is because you can keep adding additional. The more data that accumulates, the more valuable that cohort becomes, and so more groups want to do phenotyping and other measurements, molecular and otherwise. And so this has been recently launched as the Humans Project, which includes these 3 groups, but it's much more than this at the annual GET conference. We've had up to 26 different tests being done on the people real time during the conference, all sorts of measurements that do at least annually. Okay, so in addition to storage and data sharing, is this once you have data sharing, you're in a much better position to look for variants of unknown significance. This is like the big gorilla in the room when it comes to clinical use of all this wonderful big data. How do we get a variant of unknown significance? I think that everything we've been talking about so far is needed for that. You need to be able to do genome comparisons, you need to have high-quality genome sequence, not shortcuts, storage and sharing. But how do we deal with this big gorilla of variants of unknown significance? Some people feel that we really can't make progress without cohorts with n of 10,000 or more. The fact is, on a regular basis, we are forced to deal with cohorts of n equal 1. For example, this young child, 7 months old, who was born with myostatin double null, rather than this being a truly unfortunate thing that you might expect of a double null of a highly conserved gene, it resulted in him basically having a musculature of Schwarzenegger coming straight out of his mother. But what you do when you have an n equal 1 problem, which is almost all the time, and since we all are unique, is you switch from correlation methods to causality methods. And one of the ways you do that is the animal models. In this case, 3 different, wildly different mammals, cows, dogs, and mice, and they all get exactly the same phenotype or very similar phenotypes that enhance muscle growth, decrease body fat, and decrease atherosclerosis. But those are animal models. The other alternative we have, slightly short of doing experiments on human beings, which is really is a much harder in a regulatory sense to get and very hard to do for checking causality of deleterious alleles. Is looking at organs or organoids. So these are diverse now, and to Lisa Institute, Don Ingber and Kit Parker, and we and others have worked together in other institutes as well to create about a dozen such tissues. Some of them are even though they're quite simple still, they're much more sophisticated than the tissue culture, which has essentially been static for about a century, which is just spreading cells in a monolayer on plastic with tissue culture meter. For example, you get the mechanical forces of the lung, which it's very important that this pulses in a rhythmic way, where by pulsing in air in the top layer, and then epithelial cells, the boundary layer, and then endothelial cells in the blood or blood substitute, and you can even have these little red dots indicate bacterial particles that can go in, or phagocyte cells that can go out through the endothelium and the epithelium and interact with bacteria. Similarly, in the gut, on the chip also has bacteria. And normally, for those who don't do tissue culture, it's not common practice to put bacteria in with your mammalian cells. It's frowned upon. That's why you put pin strap in the media. But these are close enough to real that you can